All right, class, settle in. Welcome to your final review session. We are going to power through the most critical topics in data transmission, just to make absolutely sure you are 100% ready for your exam. So let's get started.
Okay, so here's our game plan. First, we're going to dissect a data packet. Then, we'll get into the different transmission methods. After that, we'll unpack the whole USB connection process, look at how we catch data errors, and wrap things up with probably the most important topic, data encryption. Let's make sure you've got these concepts down cold.
First up, let's break down the absolute fundamental building block of all internet communication, the data packet. Understanding this is completely non-negotiable.
Now, listen up because this is a big one. This slide highlights a super common mistake I see all the time. For the exam, it is crucial to remember that data is sent bit by bit in a single stream. We call them packets, sure, but they don't travel as these solid chunks. Just picture a single file line of individual bits all marching down the wire, one after another.
So, this is the logical structure of that stream of bits we were just talking about. Every single packet is organized into these three distinct sections, and trust me, each one has a really critical job to do to make sure your data gets where it's going and can be put back together the right way.
The easiest way to think about this is like you're sending a letter. The header, that's the envelope. It's got the to and from addresses on it. The payload, well, that's the actual letter inside, the message you're sending. And the trailer, think of it like a special wax seal on the back. It runs a quick math check on the data to make sure that the letter hasn't been smudged or tampered with along the way. And this, right here, this is how the internet handles all that unbelievable traffic. Your file gets chopped up and each little piece is sent off on its own adventure. Routers, they act like traffic cops, looking at the header and sending each packet on whatever the fastest, most efficient route is at that exact second. So yeah, they arrive all jumbled up. But that's okay. The computer on the other end just uses the sequence numbers in the header to piece it all back together perfectly. It's pretty amazing.
Okay, so we've got a handle on what a packet is. Now, let's talk about how those packets, or really the bits they're made of, actually physically travel from point A to point B.
All right, here's a classic exam comparison. The key takeaway is this. Serial transmission is all about long-distance reliability, like for your network cables. One bit just follows the next, so there's no confusion. Parallel is built for short-distance speed, think inside your computer. It sends a bunch of bits at once, but over any real distance, those bits can get out of sync and arrive at slightly different times, a problem we call skewing.
Please, make sure you know the difference between these three. This is a very common exam question. Simplex is just a one-way street, like your PC sending a signal to your monitor. Half duplex is like a walkie-talkie. I can talk, then you can talk, but we can't talk at the same time. And full duplex, that's just a regular phone call, where we can both talk and hear each other simultaneously. Simple as that.
Okay, next up, let's demystify what's actually happening in those few seconds after you plug in a USB device. It feels like magic, right? But it's actually a very logical, very cool little process.
This is the secret sauce. This is what makes USB so reliable. Think of it like this. You're trying to hear someone whisper in a really noisy room. Instead of just trying to hear their one voice, what if you could listen for the difference between two voices? All that background noise affects both voices equally, so you can filter it out and just hear the clear signal. That's exactly what differential signaling does for electrical noise. Pretty clever, right?
So this simple three-step process is what we call the handshake, and it's what gives us that plug-and-play magic we all take for granted. The computer feels the device plug in, it says, "Hello, who are you?" finds the right software driver, and then they both agree on how fast they're going to talk to each other. It's simple, fast, and super effective.
Now, with all of this data flying all over the place, how in the world do we know that the data that arrived is exactly the same as the data that was sent? Let's dig into a couple of methods for error detection.
The key difference to remember here is all about scope. A parity check is a really simple spot check on just a single byte of data. It's kind of like checking if one word is spelled correctly. A checksum, on the other hand, is more like doing a word count for the entire document. It does a calculation on the whole block of data, which makes it way more robust for catching errors during a network transmission.
And please, I'm begging you, do not confuse these two terms on your exam. A check digit is for catching human data entry errors, like when you mistype a barcode number. A checksum is for catching digital errors that happen when data is flying across a network. They solve different problems, so they are different solutions. Got it? Good. All right, let's move on to our final topic, and it's a huge one, encryption. How do we actually keep our information private when it's out there in transit?
Okay, just remember this simple distinction. With symmetric encryption, you and I have the exact same secret key. It's fast, but it's risky, right? If anyone steals that one key, the whole conversation is compromised. Asymmetric is way more clever. It uses a pair of keys. I can give my public key to anyone. It's like an open padlock. You can use it to lock a message for me, but only I have the unique private key that can actually open it. This whole system is the foundation of modern internet security.
This is the absolute core concept you need to walk away with. Encryption does not build some impenetrable wall around your data. It just assumes that your data might get stolen. Its only job is to make sure that if it is stolen, it's completely useless, just scrambled, unreadable garbage to anyone who doesn't have the correct key.
And that's a wrap on our high-speed review. We've covered packets, transmission, USB connections, error checking, and encryption. So as a final thought, now that data is basically the world's most valuable resource, think about where these fundamental principles of protection and transmission are going to lead us next. All right? Now go ace that exam. Good luck.